Okay, I will introduce you, as I did with Nastasia. It's my pleasure to introduce Anton, and I should have said when I was introducing Nastasia that Anton represents, I guess I would say, the last of the first generation of QDev master's students. And after Anton, I think I'll be better at this. I think that Anton and Nastasia and Martin Kufal, who left a little while ago, were all of my guinea pigs how to advise master's students, because where I come from, there are students. And so I got a lot of two-way education during this process, particularly from Anton about, he was often quite straight with me about how the world works and should work, and I appreciate the mutual education that we received. Like Nastasia, the work that Anton did was it was hard and hard and hard and hard. And what I mean by that is conceptually hard, and what quantum mechanics is and what it can do. But Anton also had to learn to become a cryogenic engineer, a microwave electrical engineer, and a computer programmer. And nothing would without all of those things being in place and in hand. And so, whereas I guess some people do their academic careers or even their getting really good at one thing, that wouldn't have worked here. You needed to get really good at about 5 things, and you did. So tell us what you've done.
All right. So I'll give a short talk, half an hour, about my master's thesis about scaling spin qubit devices in gallium arsenide. And the outline presented here, I'm going to briefly introduce you to a concept of quantum computer. So the whole idea why we do what we do in general, the whole field. Then I'm going to tell you about spin qubits, so basically implementation of the quantum computer in spin, in electron spins. And I'm going to shed some light on the motivation of my particular project. So what my particular focus was. And I'm going to show you how we implement them, shortly about how we fabricate them and measure. I'm going to introduce you to the results that we succeeded in measuring, and some conclusions about and further outlook. So, quantum computation. We're all familiar with the concept of Moore's law, at least we've heard about it, which is basically a trend from the 60s that tells that computing power increases twofold every 2 years approximately. And since then it really has, and now we have very powerful computers with billions of transistors, with billions of qubit bits on one single processing core. Unfortunately, or fortunately for us, there are still problems that we cannot really solve in classical computers, and those usually have a lot to do with physics and the properties of nature to exist in superpositions and have more degrees of freedom that are viably simulatable on a classical computer. So here is where we come in, where the quantum bits come in, which can, just like a classical bit, can be both a 0 and a 1, represent a 0 and a 1. But unlike the classical bit, it can exist in superposition of the states. And basically, a state of a system would be a superposition of zeros and ones. So at any given time, a qubit will exist in any and all states between a 0 and a 1. And you would think, like, how can we work with this for computation? Well, one of the properties of quantum mechanics also says that if you measure the system, it will actually collapse to a single outcome. And this single outcome will be characterized by probability. So in this case, the probability for getting a 0 will be a squared. And the probability for getting a 1 state would be b squared. And of course, the total sum has to be 1. So now if we connect multiple qubits in series, well, they can not only exist in superposition of their internal states, but also of all the superposition of all the qubit states together. And this is a very handy property that is called quantum parallelism. Basically allows us to make computation on all the states of the system, well, all the possible states of the system at the same time, and get a single outcome, where a classical computer will all the possibilities single-handedly to obtain the result. The most, let's say, infamous algorithms that were developed is the infamous Shor's algorithm, which allows us to factor a product of two prime numbers very efficiently, which scales polynomially in time as opposed to exponentially in time for a classical computer. And of course the quantum simulation, as Feynman said, it probably makes sense to simulate a quantum system using a quantum system as opposed to classical. Right. So to go back to one single qubit, since we noticed that the probability of getting each of them is 1, we can imagine a state of a qubit as a vector in this two-dimensional basis, and we can plot it in a sphere with poles assigned as 0 and 1 state, and any state of the quantum system will be represented by a vector on this sphere as shown in the picture. And this also helps us to visualize all the operations we can do to a quantum computer very graphically and handy, because quantum mechanics think of as such. So say as an example, if we want to flip a qubit from a state 1 to state 0, how we can see this is that it's just a flip on the Bloch sphere around the x-axis, which gives us a flip, and there are operations that can be done to manipulate it to any position. Right. So essentially, any two-level quantum system can be used as a quantum computer. Unfortunately, there are some systems that are just better at it. So we're all familiar with the concept of, and in principle, sure, we can use that as a quantum bit, being in a superposition of being dead and alive at the same time in the box. Unfortunately, it fails at a very particular criteria of being initializable, since it's easy to imagine to initialize a cat as being alive and make it to rotate into being alive and dead and then get the result. But the opposite is slightly harder to achieve in reality. So there are several very important criteria, and the one that I was focusing on was the scalability. To some extent, was about scaling these systems beyond one single qubit. So one of the more real implementation of quantum computation was proposed by Daniel Loss and David DiVincenzo in '98, which suggests to use a spin of a single electron as our two-level system, so basically spin up or spin down as a basis for quantum computation. Now the energy level, well, the energy of a single spin is degenerate for both spin up and down, but if we apply an in-plane magnetic field, the energy will split, being aligned or anti-aligned with this magnetic field, which gives us the splitting between our 1 and 0 state. And you can not see the Bloch sphere on there. This is a Bloch sphere, you just have to believe. But it doesn't matter. Then if you apply an oscillating magnetic field perpendicular direction, which measures the frequency of the splitting, you will be able to flip the spin around very efficiently. And by controlling the phase of this oscillating field, you can basically reach any point on this Bloch sphere, as you can see over there, using those control axes. Now, having just one qubit is great. Having two qubits is, well, obviously better, since you need to be able, for a quantum computer, you need to be able to do something called the universal set of quantum operations, which the simplest set consists of any all single qubit operations and one 2 qubit operations. And so they proposed back then to use the exchange as our driving force for 2 qubit operation, and it works by, if you turn it on and off with a particular frequency, and this frequency so the particular frequency, the particular length of that exchange, you would be able to do a slot gate. Basically, you'll be able to, if you turn on for long enough time, the spin will flip, which gives you a 2-qubit operation. Right. So there are several problems when implementing this in practice. Well, not real problems, but challenges. Say in this implementation, a very theorist-like picture, without any kind of, well, let's say, realities of the experimentalist they have to deal with, like say being able to sense which spin it is probably requires a sensor nearby, and also having 2 qubits very close to each other. Say you want to control this qubit, the interactions that which would be probably electrical, to this qubit will also affect the other qubits. So one of the things that I was looking at is implementing some kind of a long scale interaction. So here you can see I'm taking the same concept of here. I'm just leaving them apart. So this is now a left spin and right spin, similarly confined by electrostatic gates. And now, so they're far away from each other. I'm coupling them via something, which is this is a block. And one of the recent proposals suggests making this a block a multi-dot, in which case, at a particular tuning, depending on these parameters, this is a quantum dot, and these impurities represent each quantum dot. You would be able to get an exchange interaction between them, a long-range exchange interaction that is very reminiscent of super exchange, I think let's say the 4th order or something like that. Which will essentially give you the same property of being able to make a 2-qubit gate, but now at a distance. And additionally, just purely physically, it gives you more space to work with. So now say you want to place a sensor somewhere nearby, now you have all this extra space, or all this space that's freed up by this coupler to do that. So I've been talking a lot about quantum dot. What is a quantum dot exactly? Well, a quantum dot is a zero-dimensional system. In this, we work in 2-dimensional electron gases, and now we confine this system to a zero-dimensional system, which is characterized by the tunnel barriers that we control in here, and the occupation as expressed in chemical potential, of which each occupation has its own chemical potential, and we can control that chemical potential by the voltage on the middle gate, which allows us to load or unload electrons from the quantum dot. So if you apply a source to drain bias, normally a current will flow, but since we are restricted by tunneling, we are restricted by the tunnel barriers, it will only flow in the situations where you have a chemical potential level inside your bias source drain bias window, as shown here. There's a level inside. If there are no levels inside the source drain bias window, there will be no current flowing, and because of the repulsion, Coulomb repulsion of the electrons inside the quantum dot, essentially, that's why we call it a Coulomb decay. And using this, we can also, well, unambiguously determine the occupation of quantum dot by just completely emptying it and then counting upwards, or determining the relative occupation as shown here. Say we call this n, and then after each Coulomb blockade or Coulomb oscillation, we would load an extra electron into or out of the dot, depending on where you go. Yeah. We can extend the system to having 2 quantum dots in series, and now it's the same thing. We have a source and a drain potential, chemical potential, and then we have 2 quantum dots with each its own gate and its own set of chemical potential levels inside. And one particular effect that we'll be focusing on is that phenomenon called Pauli spin blockade, and the principle behind this is that, first of all, to get transport through the double dot, there should be a chemical potential from each dot inside the bias window. So as shown here, so here you have a certain sort of drain bias window, and now you have an energy level inside this sort of drain bias level for both dots, and you see current flow. Now, in a quantum dot, because of the Pauli exclusion principle, 2 electrons cannot occupy the same state if their spin orientation is the same. So basically, you can form either a singlet or a triplet. So a singlet would be anti-parallel electrons, and the triplet would be aligned electrons, characterized by different energies. So a singlet with this bottom electron, the next electron that would be in the singlet has this chemical potential, and the triplet would be higher in energy. So it would be up here if they were in the triplet. Okay, now we can tune the system into a situation where our triplet, the energy cost of adding a triplet to the system would be outside the bias window. And what this does is that, so at one bias, only the singlets can tunnel in, but because there's an infinite sea of electrons over there, it would still get current through it. It will tunnel in and outside. Now if we reverse the bias, from this side, any electron can tunnel in because there's a chemical potential level there. But now, if it is a singlet, or if it makes a singlet in the right dot, it will be able to tunnel in onto the singlet level and then go outside. But if it were to, if it would form a triplet level with the electron in the right dot, it will not be able to tunnel, blocking the current completely when you measure transport. And you'll be able to see that in a typical measurement over there, where the axis could be the gate voltages for, or will be the gate voltage for each dot. So the right and the left. And there would be current in one direction corresponding to this situation, which is flowing, and it will be blocked in a case where a triplet is too high. This is a very important property that we use for determining the spin state of a tunneled electron, and I will come back to that later. It's called spin to charge conversion. Now, I've showed you Coulomb oscillations, and this is something we can use to charge distant charge, to sense distant charge. That's using oscillations. So imagine we're measuring transport through this Coulomb dot up there, and if we take a sweep with the gate voltage, it would give one of these two curves. Unfortunately, they have the same color. There are two different curves. You can see they would give oscillations as you would expect from a quantum dot, but now it's a real picture, so it's a little messier. But now, if you change the occupation of this dot by a little bit, so by say by 1 electron, it will suddenly exert a different electric field, because there are more electrons in that quantum dot, on this quantum dot we are sensing, and you could repeat the same measurement without changing anything to this sensor dot on top. What will happen is we will see that the same Coulomb oscillations are slightly shifted. And we can use this feature to sense a change of occupation of a target dot, measuring the transport through the sensor dot. So it is done by, say, we set a gate voltage of a sensor dot to a particular region, let's say it's N, and now we're measuring 0.6 nanoamps of current. Now, if we change the occupation of the bottom dot by 1, we're suddenly looking at the other curve, and that curve at the same position now just shows just a little bit over nanoamps in current. And this is something we can measure very efficiently, and we can see these changes basically to sense occupations even over longer ranges. Now we can extend this to 2 quantum dots, and same as previously, changing the occupation of this differentiated plot. So we're looking only at the changes in conductance. Change the occupation of this quantum dot, you would see lines that correspond to a change, a new electron jumping in or out. And the same when we sweep the gate on the left side, we would see, and this is the left in the graph, we would see again lines corresponding to electrons jumping in and out. And they are tilted because of proximity. When you sweep this gate, it will also affect the occupation of the right dot, hence the slope. And this is a very characteristic signature of being tuned a double dot. In the same way as we have determined the occupation for a single quantum dot, we can determine the occupation for a double quantum dot also unambiguously. In the same way, we empty it up and we can fill up with how many electrons we want. And even more, we can extend this system to multiple quantum dots. So here I have 3 and there I have 4, and with 3 the system is
There's a blue one, the chalk.
So now imagine we have 3 quantum dots and we're moving the outside flanges. So basically we're controlling the chemical potential of the outside dots, and we still see the same picture. So this is the right and this is the left, and we see transitions that correspond to the right and the left, and the same but now we also see the additional diagonal line that comes from transitions from the middle quantum dot, because it's now equally spaced from the outer flanges, and we can hereby see its signature of being present in the system as well. And similarly, this is a picture from our collaborators in Tokyo, where they can do a 4 quantum dot array and distinct slopes, allow them to know what the occupation of the system is and where the electrons are. No, so how do we do this in practice? This is several of the quantum designs that we've been making in principle. So first of all, our electrons live in 2-dimensional electron gas. So basically a sheet of electrons that is created in the interface between the gallium arsenide substrate and the aluminum gallium arsenide, which is a different kind of semiconductor. And it originates there because these two semiconductors have a conduction band offset, which deforms the energy band in a way which creates a triangular well. Now, you lower the temperature enough, and the electrons can only exist in this triangular well, hereby confining them to only 2 dimensions, which is why it's called a 2-dimensional electron gas. And now we contact this by putting it on ohmic contacts, which is basically a big slab of gold which we put on top, and we heat it up to 420 degrees, and the metal just sieves down through the structure, making electrical contact. And we could find them through quantum dots using electrostatic gates, which are placed on top. And now when we put voltage on them, they will create electric fields that basically make it unfavorable for electrons to be present directly underneath these gates. And if you make it into a paradigm, you can find them to where you want them. But then this is how it looks in reality. It's just a piece of metal. And then when the device is made, bond it up to a sample board, and here you can see the device in the middle, small square, and all the wires connected electrically from all the electronics we have to the device. It's approximately 2 by 3 millimeters or so. And then we load it into the cryostat, which is this can over there, which basically is a helium-3, helium-4 dilution refrigerator that is able to cool down the sample to millikelvin temperatures, a typical temperature that we worked at 40 millikelvin. And from here on now, all the communication with the sample is purely electric in nature, and we can do DC communication, just slow or fast. Yeah, that's how it looks inside. So with metal plates named by the temperature at every stage until the base temperature, and here where the sample sits. Right. I'm gonna show you the device that I've been working on is one of them, but I'm gonna present you some results from. So this was originally intended as a device made by Nastasia, by the way. And it is intended for a number of experiments. So first of all, it can house a triple dot qubits. The top and the bottom section of the device, or any other kind of qubit implementation. So a double dot qubit will also be able to exist, or a single dot qubit. Of course, you're free to tune as you wish. And it can be coupled to this large dot in the middle, which is basically what I was going to look at some point at the time, to be able to couple whatever qubit you tune up in the bottom with whatever in the top. And originally it also contained micromagnets that could be placed down here, which would allow us to introduce magnetic field gradients into the device. But unfortunately for this particular device, the micromagnets didn't come out. And of course, here are the quantum dot charge sensors that we use to sense the charge dynamics inside the quantum dot. So the first thing we did when we cooled it down was to see if we can make this huge jelly bean structure. And by measuring transport from here to there through the jelly bean, we're able to tune up a quantum dot. Now it's a function of 2 gate voltages, which are these two. And you can see it shows regular Coulomb oscillations. Then we turned on all the gates, in the bottom, were at 0 volt. Now we turn them up to a certain setting, corresponding to having a double or a triple dot. And because we couldn't measure transport through them anymore, we had to tune up a charge sensor, an additional charge sensor just close to the jelly bean to sense its charge configuration. And what we saw was a large dot, which is characterized by very small level spacing. So basically, here it is. Unfortunately, one problem that we could see right away is that it's very close to 0 volt. And it's not a big problem in this region, which shows kind of regular charge transitions. But it is a problem if you go further down there, you try to empty it of electrons and make it smaller, it will break up into smaller quantum dots. And you can imagine, I get an intuitive feeling for this, say if your quantum dot is a big balloon and you only work in 2 dimensions, so look at it from the top. So normally what we like is having these depletion gates deplete all the electrons underneath them and then push from the sides. And by pushing this balloon from the sides, what you would see is that it's getting smaller. And that's essentially what we imagine happens with these quantum dots. But now, because we're working with this big balloon, the electrons still live underneath the gates, because you need a larger negative voltage to deplete them. So basically pushing on this balloon from the top, and what happens if you do that is basically goes around your hands and breaks up into smaller kind of patches of electrons. We can even probably see something like, looks like a triple dot signature, which is unwanted in this case. But of course we can always operate in this region. Then we looked at the double dot and turned on playing with these gates at the bottom, and we were able to tune up a beautiful double dot. Again, measuring transport from here. You see the signatures, a distinctive signature of a double dot, which is these 2 sets of Coulomb oscillations, but so that they affect each other. And as you see here, if you go further down in negative voltage, the level spacing of the quantum, as the dot becomes smaller, its cell capacitance becomes larger, and the spacing between the energy levels becomes also larger. That's why you don't see as many energy levels entering sort of drain bias window, and so you only see current at the cross points. And now, examining these cross points, we were able to find a region which exhibits spin blockade behavior, and as you can see here, for a negative bias configuration, we still see some transport through that crossing, and if we reverse the bias, we only see transport from the sides, similar to the figure I showed previously. Now here we also want to play with the thing that I told you before about the spin to charge conversion, basically being able to sense what this spin configuration of this electron that we're traveling through was very, very quickly. And so we implement, we use this spin blockade, but now we use fast gates, so very fast operation in the order of nanoseconds, to shuttle the electrons around and see what the state is. And this is done in this way. So we start over here in the 0, 2 region, so 2 electrons in the right dot. And because it is tuned to spin blockade, they would be in a single state, so anti-aligned. Now we spit out the electrons over the lead into O1 region. Into O1 region, so it basically kicks it out, and we empty it. And then we load a different electron into the neighboring dot, into the left one dot. And now this electron can either be a singlet or a triplet, because it comes from the lead. And then by the quick pulse, we make a tunnel from the left dot into the right dot, back to where we start. And now similarly to how I described it with the spin blockade, if it is anti-aligned with the electron already present down here, not down here, but down here, it will be able to tunnel, and you see this normal transition. But if it's in a triplet state, it will not be able to tunnel, and what we will see is this part of this charged state, which is, you see red versus green down here. It will kind of spill into the region of the 0, 2 occupancy, which is basically dragging the charge state over the transition because it cannot tunnel through. So your charge sensor doesn't pick it up, or it picks up no tunneling went for that gate position. And then we can do it very fast, a lot of times, and after 4 milliseconds we're able to distinguish which ones were the singlets and which one were the triplets. I just make a nice plan. So here you can see the. So this is the. So this is the singlet, and this is going to be the triplet charge state. You can clearly distinguish between the two. So nice. And lastly, we also tried out to tune a triple dot in this device. And it was successful. By just turning off these gates, and you can see that triple dot signature is very nice. Shows that it can be done on this device. So as a conclusion, we developed a robust recipe that can be scaled to anything. So these are some of the daring ventures into fabrication world. So this one shows, for example, the 15 quantum dots in a row with 5 charge sensors designed for 5 qubits, and this is the one I measured together with Johannes earlier with 3 triple dot qubits connected by jelly beans, each having their own charge sensor. Of course, this is the butterfly device. We found out that the cross coupling of the gates, as predicted, is pretty important and poses a big problem. So, for example, in this device, it was very hard to tune up a neighboring qubit without affecting the first one by just ramping the gates up and down. And the same was seen here for the jelly bean, as well, basically we could no longer deplete everything underneath the gate without completely destroying the dot. And over the years there have been developed several solutions that have not been implemented, unfortunately, yet in these devices. Some of the solutions, one of the solutions is introducing the multi-electron coupler, you should say. So it's a big quantum dot, which, because it has so many electron pairs, would there are papers that say it would screen the electric fields from the neighboring qubits, which is one of the solutions. The other solution is putting a big layer, a huge top gate over the whole device, which would absorb some of the field lines coming from the gates, basically screening the integrations via. And the last solution that's being tried out right now is to introduce a accumulation gate, so a different polarity gate inside the quantum dot that would attract electrons to that place, so you can push harder with the walls without completely destroying the puddle of electrons that you're actually interested in. And it seems to be pretty successful. So for this particular device, of course, another solution would be to just move these gates further back. Is also a solution. So we've found a number of device optimization tricks from these cooldowns. And well, of course, there are lots of stuff to do in the future with these devices or similar. Some of the things that I think would be very interesting is to be able to create different types of qubits on each side. And say have a positive Vincenzo qubit up here, but a exchange only down there. The exchange only is very fast. It's purely electric in control, so it can go up to tens of gigahertz estimated, while a lost Vincenzo, fully isolated, because it only is operated by magnetic fields, has longer coherence times. So you can imagine doing fast operations on the bottom, then saving this state in the lost Vincenzo qubit, then coming back to it after some time, or something like that. So it's lots of steps, lots of interesting things. And of course, show this exchange that is predicted. Just a small thing. And yes, thank you for your attention.
Thanks, Anton. This talk is now open for interrogation by the public. Well, if we could be the public for a minute. Some of these designs that you showed with lots of qubits on them, were they successes or failures or learning experiences?
They were more or less than a success. So in principle, yes, they did work. So say this long 15 quantum dot device, you could tune up double and triple dots in any position. Mm-hmm. Unfortunately, if you tried to tune up two of them at the same time, they would suffer either from very high cross-coupling, just from the neighboring gates, or more importantly, because you want to be able to load electrons in and out of these quantum dots. Having just one big sequence of quantum dots makes this very hard. So that's why we transitioned from these kind of devices to these kind of devices, where here you will have a puddle of electrons that you can tap into should you want to load into this triple dot.
Are those devices, let's say that guy on the bottom right,
yes.
Is that still alive, sitting in a drawer somewhere?
I think so, yes. Those guys should know. So it was a bit shaky, but the design exists and it can be fabbed anew on a better material. Maybe if the more shallow material, the one that we used lately, are better for it.
Yeah, I was going to ask. That was sort of my next question, which was, let's say you had a hankering to measure again. Would you put these devices back in the fridge and measure them again, or what would you do if you had the next 6 months to measure a device? Would you fab new devices knowing something new that you know, or would you say, well, I'm actually more sophisticated in measurement now, I think I could do perfectly good with these?
Now that we are pretty well versed in fabrication, it doesn't really take that long time. So knowing everything I know now, I would fabricate a new generation that kind of slightly improves it with small tweaks to the design. So here I would put ohmic contact down here, for instance, so I can ground that if I want to, or have a fresh pool of electrons every time. Here I would push them back.
I see. So tweaks.
So small tweaks.
And you say the fab is so easy that in fact
it's basically
there's no big headache for small tweaks. You just go do them.
No, just go and do it. So I don't see a reason to recool the old devices because they all had that problems.
Well, I have more questions, but maybe yeah.
What I'm just wondering, has it been done on gallium arsenide? Maybe from another group putting a screening top plate on top?
We did it.
You did it? Oh.
Yes, I can show you some of the data that I measured together with Johannes. Let me see. Whoops. That wasn't the attention. Maybe before. No? So here you see this. We have a large metal gate on top of just the bottom side of the device. So it's a in a row. I think it was a triple block gates. And here we don't have a metal gate, and here you can see this big metal gate which is separated by a layer of oxide over the actual Qubit gates. And now we're just doing pinch-off tests, 2 dimensions. So this is gate 1, this is gate 2, so these 2 gates, and the same here for the screen device. And it seems like it actually, because you would, the less slope you have, the less cross-cutting there is.
So perfectly uncross-coupled would be square.
Yes, perfectly uncross-coupled would be square. Of course, this is a very small sample size, but definitely worth revisiting. Why not? It's easy to fabricate, and it is.
Okay, more questions from. Okay, if not, then we can move to phase 2 of this, which I now know proceeds as follows. During phase 2, the sensor and I will ask questions, and Anton will answer them. And now, it's a good opportunity if you as I said in the Stasi's talk, if you don't like the sight of blood, or you have somewhere else that you have to be, this is the end of the formal exam. I mean, the end of the formal presentation. Now it's like exam phase. If you're curious what that looks like, if you're the kind of guy who likes to slow down by a car wreck or something, this is you can stick around and watch this part of the process too. But if you don't want to do that, now's a good time. Thank Anton again, and then you can go or stay.